We say that f is continuous at t in A if for all epsilon greater than 0, there exists delta greater than 0, right? Such that whenever distance of a point in any point and x is less than delta implies, I think you all are familiar with this definition. Is less than epsilon. Now this definition can be, so this is a metric space, right? If we take a usual metric, then this definition can be transformed to this. Like we know that in a usual metric, distances transfer to mod of x minus p, right? So our above definition can be transformed to whenever x minus p is less than delta, this will imply, sorry, I have made a mistake of it. It will be d of y fx comma f. This will be less than epsilon for all x in x, right? Now, if a function is continuous at a point, say at a point P, right? Then that point P is either a limit point or an isolated point, right? So, because any point in real is either a limit point, there is a theorem like any point, because any number, real number is the union, any number is either a limit point or an isolated point in real number, right? So if P has to be continuous at, F is continuous at a point, then P will be either a limit point or an isolated point. Now if P is a limit point, then by F being continuous is same as saying that limit x tending to P fx equals to F. Now, if P is not a limit point, that P is an isolated point. So by definition of isolated point, there exists some say delta prime, which will be greater than 0, such that any open ball at P with radius delta intersection with A is equals to P, right? This is what definition of isolated point is. Now, if I take this delta prime, right? Then only x in A which satisfies this relation, right? P of xy is less than delta prime is P, because P is an isolated point, right? So there will be no point in that neighborhood except that point P, right? So that is P of x comma P will be less than delta prime, right? It's same as saying that by definition, this will imply D of fx comma fp. This will be 0 because fx and fp will be same because there is no other point except p, right? Because p is an isolated point. This will be automatically less than epsilon. So suppose these we have metric space from x to y, right? So what we have got, right? Observation. Observation is if A is such that every point of A is an isolated point, then any function f from A to y is always continuous. So this is what we have got. If A is an isolated point, so by definition there will be some delta prime, right, greater than 0, so that this relation is going to hold, right? So if I take in a above definition this delta prime, then the point which satisfies this relation is only P, because P is the only point which lies in this neighborhood, right? So by default, this is going to hold, right? So by default, it's going to hold means so we know that example for that n z, its all its points are isolated point. So no matter what function you define, if you define any function f from n or z to any set, right, say y, so this function is automatically going to be continuous, which means that if p is any point, if p is an isolated point, then any function is automatically continuous at p. So only problem the function is going to face that if p is a limit point. So from conclusion is that any function will be discontinuous at limit, because if it's an isolated point, it's automatically continuous, right? So this was the brief definition of continuity. Now we'll give some sequential definition of continuity, right? Because it's important to also go through the sequential definition of continuity. The sequential definition of continuity says that if F is a mapping from, we'll take the same sector, X comma D, dx, okay, and Y comma D are matrix spaces. And F is a mapping from X to Y, is continuous. This implies if and only if for every sequence any sequence xn tending to x naught, in x, this implies f of xn tends to f of x naught in y. So if f is a continuous function, and if you have any sequence, suppose where xn is a sequence in Ax, right, and f of xn is a sequence in y. So if f is any function, continuous function from x to y, then any convergence sequence that is continuous map sense this, what does this definition says that any continuous map sends convergent sequence to a so any continuous map sends convergent sequence to a convergent sequence. This is what sequential definition of continuity is. So the question arises that does continuous map sends Cauchy sequence to a Cauchy sequence? And the answer to this is no, right? And the example which you can just give the example as, say you have a like let's take a metric in R, right? So take x as 0, 1 and y as a real number R, right? And suppose f is a mapping from x to y defined by f of x is equals to 1 by x. Is a continuous function which is continuous on 0, 1. The open interval 0, 1, right? And also we know that one comma n is a Cauchy sequence. You can just go through any standard book, you'll find this example where 1 by n is a Cauchy sequence, not 1 comma n, it's 1 by n. It's 1 by n is a Cauchy sequence. But what is f of 1 by n? Which is n, which is not a Cauchy sequence. So what does this says that? Continuous map does not send Cauchy sequence to a Cauchy sequence. So before moving on to some practical examples, we'll just briefly discuss what homeomorphism is, because these are very important terminology. We'll discuss what homeomorphism is, right? We will take same setup like x dx, y dy are two matrix spaces, right? And f is a mapping from x to y. Then we say that f is a homeomorphism. If number one, f is continuous, f is bijective, and number three, f inverse is also continuous. So this is the definition of homeomorphism. Also, we have one result like it's a very standard result. If we are not going to prove this, we rather discuss on application of this theorem. Continuous image of a compact set is compact, right? So there is one important result, like it's very important result. Which says that, which is known as continuous inverse theorem. Continuous image of a compact set is compact. It can be found in any standard book. Truth can be found in any standard. Very common theorem. Any standard, right? For example, you can follow a postal, SK Mapa. If you can follow these two books, all the theorems will be found in this book, right? So rather than we'll prove this continuous inverse theorem. What does this say? That if f is a mapping from I to R, where I is an interval, right? It can be any interval, closed, open, both open and open, whatever. If any is be continuous. And also strictly monotone. F is a mapping from I to R, which is continuous and is strictly monotone. Then there exists an inverse of F inverse from f of I to I, which is also continuous and strictly monotone. In the same as that of that is, if f is strictly monotonic increasing, then f inverse is also going to be strictly monotonic increasing. If f is strictly monotone decreasing, then f inverse is also going to be monotone decreasing. Right? So this theorem says that if f is a mapping from I to R, where I has to be an interval, be continuous and strictly monotone, then there always exists an inverse of f from the range of f to I, which is also continuous and strictly monotone, which is monotonicity is in the same sense as that of f. So it's not difficult to prove this because this theorem is not present in or you can't find this in book. So I'll give just a tutorial proof of this because it's quite important theorem and you need to visualize why it's happening. Right? Okay, now I have to show that f is no f is a mapping from I to R, right? This given is continuous and monotone, right? Then f, which is a mapping from I to f of I. This function is onto function, right? Because f of I is range of f. So this from function from this I to f of I has to be onto. No. Since without loss of generality, we'll assume that what we'll assume is f is monotonically, f is strictly monotonically increasing. We'll assume. We'll prove this theorem assuming f is strictly monotone increasing, right? Now, suppose this is x-axis, this is y-axis. Now f is increasing and it's continuous, right? Suppose the function has to be of this type. It's increasing, like it will keep on going up, and also continuous, that there will be no break, right? And it's monotonically, strictly monotone. Strictly monotone means there will be no, like the graph will be totally like in upward direction, right? Totally upward direction. The graph is not going to be of this form. Like it's going up and suddenly it's taking a straight line and again it's going up. This thing is not going to happen. If this happens, then the function is not strictly monotone. At this point, the function fails to be strictly monotone. So what I mean that continuity plus strictly monotone or monotone increasing, this implies 1, 1. So f is continuous and strictly monotone implies f is 1. Because you are not going to face this kind of situation. Right? If it is not 1, 1, then you are going to face this type of situation. So for distinct value of x, you are getting the same values of y. So since f is strictly increasing, your graph is something going to be like in upward direction. So for distinct values of x, you get distinct values of y's, right? So always you have to note that continuity and strictly monotonicity, whether it's monotone increasing or monotone strictly monotone decreasing, this automatically implies 1 function. So what happened? F from this to this is onto, and f is also 1. So we can claim that f from I to f of I is a bijection. Once it's a bijection, then there exists an inverse. So there exists an inverse, that is F inverse. F inverse from F of I to I. So existence we have totally shown that existence is very yes, there is an existence of such thing. Now we have to prove that F inverse is also continuous and F inverse is also strictly increasing, because we have assumed F to be strictly increasing. So suppose take 2 points y1 and y2 in F of I. I have taken y1 and y2 in F of I. So what happens? So there exists x1, x2 in I such that F of x1 will be equals to y1 and F of x2 will be equals to y2, right? And assume that y1 is less than y2. We have to show that we have to show that F inverse, that is F inverse of y1 is less than F inverse of y2. This will show that inverse is an monotonically monotonically increasing, right? So what happens if I assume that y1 is less than y2? Then we'll have two cases, either because f we have taken x1 and x2 from I, and f is an 1 1 and onto function, right? So this x1 and x2 we have taken, it's x1, definitely it's not going to be x2, right? It is distinct point because f is 1 1 function. So either x1 will be less than x2 or x1 will be greater than x2. These are the only two possibilities for x1. Now if x1 is greater than x2, and since f is monotonically increasing, f of x1 will be greater than f of x2. This would imply f of x1 is y1, this is greater than f of x2 is y2, which is a contradiction. Because we have assumed y1 is less than y2. Now x1 is less than x2, this will automatically imply f inverse y1 is less than f inverse. So f inverse is also strictly monotonically increasing function. Now we have to show f inverse is also continuous. So is it okay to prove this theorem? Is it taking too long? Hello? Hello? Am I audible to you, sir? So to show f inverse is also continuous, right? So in order to f inverse is also continuous, we'll assume that okay. We assume that f inverse is f inverse is discontinuous at some point, right? Say at some point, say C in f of I, right? So f inverse is discontinuous at some point, C in f of I. Now f is what? Monotonically increasing function. So f is monotonically increasing and f inverse is discontinuous at this point. So f of I is going to be at this point, I is going to be this. So function will be something like discontinuous at this point, means function is moving up, having a break outline. So the C is any point outline. So what will happen is, since it's an increasing function, so left hand limit at C of f inverse of y will be less than right hand limit, because it's a monotonically increasing function, right? So for increasing function, left hand limit is always less than right hand limit. This is very basic result. So strictly less than is, so there will be this, so there will exist some point in between this. So there exists, say, any point, say x. That is, there will be some point in between this. The graph will be going to be something like this, right? Suppose, say, function is a draw properties. So function is something like this, right? It's having a break at some point. It's having a break at point C. This is f of I. This is I. This is what? It's an increasing function. This will be left hand limit, limit extending to C minus f inverse of y. And upper hand will be right hand limit, limit extending to C plus f inverse of y. And we are saying that x lies in this point, right? Now we have to know that for this value of x, there exists no point in this line which corresponds to this x, because at this point there is no point, right? It's totally a vanished point. So there will be no point for which this x is going to correspond, because there is a gap out there, right? So there exists no point in between this. So what? So this, so which will correspond to x. So there does not exist any point in between because we have taken x to be an arbitrary point. So if this does not exist any point, this implies we have taken this implies I is not an interval. Because from we have assumed that I is an interval. So f inverse is continuous. Because if I is an interval, it should contain all its points between this range, right? Since I is an interval, this between this interval should contain all its points, because I is an interval, right? So what is happening is I have a sub-interval inside I, which contains no points in between these 2 points. So this contradicts the fact that I is an interval. So this gives a contradiction. So contradiction arrived because we assume that f inverse is discontinuous. So f inverse is continuous. So this proves continuous inverse theorem. So there is another result. We have also, we just state this result. Continuous plus 1, 1 will imply strictly monotone. What we have said that continuous plus strictly monotone implies 1, 1 in above. Both these theorems are true, right? Okay, now any two interval I1 and I2 will be homeomorphic if they are of same type. Which means that this interval 0, 1 is homeomorphic to this interval 0, 2, right? This interval 0, 1 is not homeomorphic to 0, 2 because this is an open interval, this is a closed interval. So they have to be of same type. Once they are of same type, they will be homeomorphic, right? Now it looks like first one or two example. So is it taking long? I should stop or go ahead? Now let's discuss some example. Suppose we give an example, right, which has arrived in net. Suppose F is a mapping from A comma B to C comma D. And the question is, can F be onto? Yeah, it's one. So can F be onto? So if F be onto, then F of A comma B will be equal to C comma D. And this, we know that in real analysis, in real closed plus bounded will imply compact. Any border theorem. So closing any closed, this interval is always compact. It's closed and it's bounded. So F of A comma B equals to C comma D. Right? So F is, and I'm saying that F is continuous. F is continuous. So F is continuous. This is compact. Continuous image of a compact set is compact. So this thing is going to be compact. But this is not compact. It's bounded but not closed. So this is not compact. So if they cannot be an onto function from A comma B to, so there does not exist continuous onto function from A comma B to A comma B to close A comma B to, it was closed, right? If I add one more option, can F be onto? Another option is, can F be bijective? What is the problem if you face that F be bijective? Now, So it cannot be onto, so it's not going to be bijective. So another explanation you can give also, if f be bijective, I can give rather than bijective, I'll give because it's not onto, so it's not going to be. Can f be 1 on? That would be, can f be 1? Now, if f be 1 1, also f is continuous, right? So f is continuous plus 1 1. This will imply f is strictly monotone. Either it will be monotonically increasing or strictly decreasing. So this will automatically implies by in continuous inverse theorem, f inverse is also continuous and strictly monotone by continuous monotone theorem. Right? This will imply a comma b will be homomorphic to open interval c comma d, which is a contradiction. Since they are not of same type, right? So there cannot exist one function from this point, this set to this. Okay. And there are a few problems to discuss. Sir, I think I should stop now. Or I go ahead or I should stop? Hello? Hello? Yeah, yes, sir. I should go ahead or I should stop? No, okay. Okay, now we discuss a few theorems like, okay, we have there is a concept of identity theorem. It says that if f is a mapping from R to R, which is a continuous function, such that f of t is constant, which is say k, where k is a constant. And what is d? D is D is where D is set, which is dense in R. Its closure is equal to R. Then f of x is equals to k for all x in R. So if a function is continuous and it's like constant in a dense set, then it's constant in entire whole of R. So how will you prove this, right? So let A is in R. What is R? Where D is closure of set in R. So we know that they, by definition, you might have studied in or in a sequence, right? So if you have 10 sets, so there exists a sequence. So there exists a sequence say AN in D such that AN will tend to A, right? As n tends to infinity. This is a definition, sequential definition, right? So since f is continuous, then continuous function sends convergence sequence to convergence sequence. So f of an will tend to f of a. So what is f of an? We have discovered what is f of an. F of an is a sequence in D, right? And what the question says that function is constant in D. So f of an will be constant k, right? And a f of a will be like then this sequence as then f of a will tends to some okay. Just then f of n will tends to f of a, right? So what is f of a? F of a is nothing but it's going to be k, right? And what's happening is f of sequence. What is f of sequence of n is nothing but k k k which tends to k. So f of a equals to k. Now since a is arbitrary point and we have taken a from R, right? We have taken a from R. Arbitrary point so f of x is going to be k for all x in R. So this is what identity theorem says. So application of this theorem, we'll do one application of this theorem. Application of this theorem, which has also appeared in NET exam. Application of this theorem says that suppose you have two functions f and g, which is from R to R, right? And it is a continuous function. And it's given that f of x is equals to z of x for all x in D, where D is nothing but dense set in R. Then we have to show that then f is pointwise equivalent to z. We have to prove this. Now it's given that f of x is given that f of x equals to g of x, which will imply f minus g of x equals to 0 in D. Suppose I have taken f minus g is h of x equals to 0, where h is nothing but f minus g. So what's the result is h of x is equals to constant in D, where D is dense in R. So by identity theorem, what does identity theorem says here? H of x will be equal to 0 for all x in R. So what is x? H is f minus g of x equals to 0 for all x in R. This should automatically imply f is equivalent to g in R. The question was given f is equivalent to g in TNSET. Now we have shown that F is equivalent to G in R. So this is an immediate application of vertical identity theorem. So we will show one more result. Prove that if F is a mapping from R to R is continuous function. This question was also there in your exam. Such that f of x plus y is equals to f of x plus f of y. Then we have to show that f of x is nothing but is cx. If f is a continuous function and so with this condition holds, then we have to show that f of x equals to c of x. We have to prove this. So how we are going to do this? Okay. F of what we are going f of p by q. I can write this f of p by q as f of 1 by q plus f of 1 by q plus f of 1 by q up to p times. So by this linearity, I'll break this 1 by q up to p times. So what we have got is p into f of 1 by q. Now you can write f of 1 as f of 1 by q by q, which is equals to q times f of 1 by q. Right? You can like break q into 1 by q plus 1 by q up to q times. Again, using this expansion, we can prove this. Right? So what is going to be f of 1 by q? F of 1 by q. Right? So what we have got, f of p by q is equals to p into f of 1 by q. Suppose say f of 1 is a constant, so say f of 1 is some constant k. Right? So what we got, f of p by q as p by q into k. Where what is p by q? P by q belongs to rational, and we know that q is dense in R. Rational number is dense in R. Right? Q is dense in R. So by identity theorem, what it says that if this function is equal to this in dense set, then this has to be xk for all x in R. So this is an immediate application of what we call identity theorem. Okay, now I think one theorem. It's not going to. Suppose f is a continuous function from f is a continuous function from r plus positive reals, right? R plus r, and it's continuous, right? Such that f of x into y is nothing but fx plus fy. Then with that f of x is log of x. Right? We have to show this. So we prove this. This question is also, this question has also been occurred in NET, I think. Because they remember, so it might be in NET exam. So you have to prove if f is any function from r plus is positive real number, right? To r, which is continuous, and also this condition holds, right? This condition holds. Then I have to show that f of x is log x. Because we know that log is only defined by positive real number. For that reason, we have domain is given r plus. So for that, we'll assume that what they call, suppose we assume okay, we'll do this. So let's take a function, any function from suppose say z. Suppose define a function z of x as f of e to the power x. We'll define a function as g of x as e to the power x. Now f is continuous and this is also continuous. So composition of a continuous function is continuous. So this function is continuous. So the function which I have defined is nothing but it's a continuous function. So g is a continuous function. Right? So what will be g of x plus y? It will be f of x plus y. So it's f. We know that exponential breaks in this form, dx dy. And function we have given the formula, it breaks into addition. So this is nothing but f of e to the power x plus f of e to the power y, which is nothing but g of x plus g of y. So what we have got is g of x plus y equals to g of x plus g of y, which is linearity. And also g is continuous. So just we have proved this theorem, right? I will just show it to you. We have proved this theorem. Yeah, this one. We have proved that if f is continuous and f is linear, then implies fx equals to cx, right? Some linear function into x. So what g is continuous and g is linear. So g has to be equal to gx has to be equal to some c into some x, right? That is what is g of x? G of x is f of e to the power x. Has to be equal to some cx. Is the x, suppose s is given. S is what? X in R says that fx is less than equals to gx, which is nothing but x in R such that